So any combination of continuous functions is continuous. So that's one thing that I wanted to mention. The other thing that I was going to, that I didn't get the chance to explain last time was continuity on an interval. Continuity on an interval. So help me fill this in. A function is continuous on an interval if it is continuous at every, what do you think, point on that interval. So if it's continuous at every point on that interval, one next to the other, it must be continuous on the entire interval. One other item that I didn't get the chance to get to last time is the intermediate value theorem. For, of course, continuous functions, the intermediate value theorem for continuous functions. Here is the idea. Let's look at the graph. So we have a function here. This is our function, f of x. And let's suppose that I look at a unit interval. It shouldn't be bigger than that. What is a unit interval? Okay, between 3 and 4, that's a unit interval. Between -5 and -4, that's a unit interval. Between 0 and 1, that's a unit interval. So let's suppose that I know that f of x, and it's clear, the function is continuous on this unit interval. It could be smaller, but not bigger than that. So let's say this is a and b. Would you agree that this function is continuous on the interval a comma b? We don't care what it does outside, but on the interval a comma b, can we conclude that f of x is continuous on a comma b? Would you accept? Yes. Now from my graph, that's number one. From my graph, number two, would you accept if I say that f of a, if I write that f of a is a negative number and f of b is a positive number? Would you accept that too? Yes, I can change the graph and do this, of course. Would you accept this? And I'm going to call this here C, this point. So what the intermediate value theorem says, really, we haven't drawn any conclusion yet, but what it really says is this. If a function is continuous, and we say on an interval, and we say it changes, and we see it changes sign on that interval, from 1 and 2, we abbreviate IVT, intermediate value theorem. So from 1 and 2, by IVT, there exists a number C inside, this is a new symbol that I have not talked about yet, This stands for in the open interval a comma b, such that what? What is our conclusion? Look at the graph and you'll say, oh, I know what you're trying to say. Such that so if it's continuous and it changes sign, there must be a point between a and b where the function value is exactly. Thank you. That's it. There must be a point if it's continuous. Now, if it's not continuous, we're not talking about the intermediate value theorem. It's done. We don't have anything to say. But if it is continuous and it changes sign, then it must have a solution or a zero. So C is called the zero of f of x, or the x-intercept of f of x. Also, the solution, if you want another way of looking at it, the solution of f of x equals 0. But that's the same with the 0 of f of x by IVT. Here is a problem with this. IVT will not find C for us. It will only tell us you're looking for a 0, you're looking for the x-intercept, or you're looking for the solution of this. I'm telling you where it is. It's between A and B. But I can't tell you what it is. However, this is extremely helpful, and we are going to base everything on this. Not, I shouldn't say everything, but you will see where this is coming into play again in Chapter 4, where you will learn Newton's method. When we are going to get to Newton's method, you will be very nicely surprised, I hope, that you will be able to solve any equation on the planet. You haven't been able to so far. You're able to solve linear, quadratic, some cubic by hand, some natural log, exponential, blah, blah, blah. But an equation like this, you cannot. No one can by hand. But Newton's method will give us the solutions or solution to this with any accuracy that you want. 10 digits, more. And we will be using the IVT for that to start. Right before we even start Newton's method, we're going to use IVT again. So IVT has a flaw. It only tells us, it points us in the right direction, but it doesn't find C. So I think we should stop for a second and look at an example. So again, as I said, I don't have a new book, but I printed out just the exercises pages. If you want, I can scan these and post them for you, or you can find them directly in the ebook. So let's choose any, since you see here the interval is given, but the interval may not be given to us. We may have to find the interval. Here they are nice to us. They say, okay, use the intermediate value theorem to show that there is a solution in this interval for each equation. But here they're saying, find it yourself. So find where the solution is and show that there is a solution, but you will not be able to find it yet. So which problem we want to start with? Also, I just remember that I had one more item to work on in this section, which is a problem with the parameter. And that is a very important type of problem. Okay, I'm ready. Would you like to choose? You want to choose one with the when the interval is given, or you want to choose one when the interval is not given?
Can we do one without the interval given?
Without, you said?
One without the interval.
Okay, very good. So I'm going to choose 59, or you can choose 60. It's up to you. 50 or 59 or 60.
59 is fine.
Okay. So we have cosine x equals x to the third. Good. So my first step is this. Create the function. I don't see a function yet. I see two functions. Create one function. I wanted to write f of x directly. So here's the function. So then f of x is cosine x minus x cubed. In calculus, we do not put in cosine or trig functions, in this case cosine. We do not use degrees. So we use radians. So please remember to set your calculator to the radian mode. So go to mode and make sure your calculator is in radian mode, not degree. After that, we will put this function in y equals. So y equals cosine x, close the parenthesis, minus x cubed, caret 3. And then we go to second and table. We don't know what to expect. Yes, we can graph the function to see where the solutions or solution appear to be. So that's one option. What I normally like to do, unless the solution is 1500, what I like to do is just start normally with 0 and 1. I found it. So at 0, so step number 2, f continuous on 0, 1 as a combo or a difference of continuous functions. And yes, if you're asking me if you have to write this down, yes, you have to write this down on your test paper. So not the fact that I have to create one function. That's very clear to me. Once you put everything on one side and you write f of x, that's very clear. You don't have to write radians, of course. But number 2, you have to say that this function, f of x, is continuous on 0, 1. Why do I pick 0, 1? Because I have exactly what I need. Between 0 and 1, the function is at 0 is positive and then 1 is negative. So obviously, that's all I care about as a difference of continuous functions. This is continuous everywhere and this is continuous everywhere. So the difference is continuous everywhere. Okay. And then in part 3, I will say that f of 0 is a positive number. I don't even have to copy what it is. And f of 1 is a negative number. From 2 and 3, by IVT, there exists c in the interval 0, 1 such that f of c is 0. And it's done. Now, if you ask me what is c, I'll say, sorry, I don't know. I know it's somewhere between 0 and 1, which is huge.
Can you go back to the one page? I wasn't finished copying.
Oh, yes, I'm sorry.
No problem.
Of course. Always stop me. Okay, I would like to illustrate, and I would like to let you decide which function you want to look at. And also, I would like to look at a function with a removable discontinuity. Is this clear? Is the intermediate value theorem clear? Obviously, it requires the function to be continuous and change sign. If the function is not continuous or does not change sign, IVT is not applicable. Any questions?
Yeah, I have one question.
Please do.
Does it have to be between two whole numbers, like 1 and 0? Can it be between, like, 0.5? Like, can we get more accurate, or does it have to be...
Absolutely you can. That's what I said. Not more than a unit interval. So if you say the solution is between 0 and 10, that's not acceptable.
Okay.
But if you say it's between 1.5 and 1.7, awesome.
Okay.
But not more than a unit interval. Very good. Okay, so would you like to start with a removable discontinuity to illustrate how we remove the discontinuity, or a parameter situation? Say it again. The removable? Okay, very good. So let's take a look at 51. I don't know if there is another problem similar to this. But we have A, B, and C. I don't know. Let's do A. Doesn't matter. F of x equals x to the fourth minus 1 over x minus 1 for A equals 1. So we are still in 2.5. So which of the following functions f has a removable discontinuity? If the discontinuity is removable, if it is removable, find a function g that agrees with f for x not equal that value, and it's continuous at a. We're going to get to that. So let's see what we get so far for this. Well, obviously, from the very beginning, I would say that x cannot be, for this function, definitely,
1.
Excellent, thank you very much. So I'm going to try to simplify the function now. And I know that x to the fourth minus 1 factors how?
X squared equals...
Very good. You're on the right track. X squared.
plus 1 x squared minus 1.
Excellent. This is not factorable, but this one is. So we can continue. X squared plus 1 and yes, x plus 1, x minus 1. Because I already stated the necessary conditions or restrictions on x, because of that, now I'm allowed to simplify. And I get the final simplified form of x squared plus 1 times x plus 1. I write myself a note right here next to it, if x does not equal 1. Some time ago, last week, we said that something happens. It's a specific situation in which a factor from the denominator and the factor from the numerator go away. And the function is still undefined at 1. But when a factor from the top and 1 from the bottom, they go away, then we know that something special happens there. What is that? What did we say? What happens there? Anyone remembers? What did we say?
There's a hole in the ground.
Excellent, thank you very much. So we already know that this is a hole in the graph. Very good, awesome. So if it's a hole in the graph, the function is not continuous at 1. It cannot be. It's undefined at 1. So therefore, I know that f of x is discontinuous at x equals 1. Knowing that, why do I know that? I mean, the limit from the left and limit from the right would be the same. but it will not be equal to the function value. Let's write that just to refresh our memory. So continuity at a point. So a function is continuous at a point. For this one, I'm going to write 1. As x approaches 1 from the left, from x squared plus 1, x plus 1 equals limit as x approaches 1 from the right of x squared plus 1, x plus 1 equals f of 1. We know that these two are equal, but I'm going to have to cross this equal symbol. It's because it's not correct. It's false. Cross it out, right? So this piece, 1 squared, 1 plus 1, 1 plus 1, 2 times 2 is 4. Obviously this is also 4, but this does not equal f of 1, because f of 1 does not exist.